Today we're going to be talking about beam deflection. Now, what we have to first talk about is what is a beam member. A beam member is any of these small, thin pieces of metal that support an overall larger floor or ceiling. They're relatively small in comparison to the building. So you can think of them, we commonly refer to them as beams, but they can also be these columns or these diagonal pieces and other supports. Those are also called members as well. Now, moment of inertia, symbolized by the letter I, is a property of its shape. We can use the moment of inertia to see how stiff an object is based on its geometrical shape. The larger the moment of inertia, the stiffer and the harder it is to bend. Now, those units are going to be either in inches to the fourth power in imperial, US standard, or they're going to be in the metrics. It could be millimeters to the fourth, centimeters to the fourth, or meters to the fourth, depending on which units you use. Now, the equation is this. It is base times height cubed divided by 12. Notice the cube on the height. That means that the height plays a much larger effect in this overall moment of inertia than the base does. The base plays very little in comparison to the height. So if we look at these two, if you take a 2x4 and put it in what we call, this is called plank position, and you apply a force downward into the beam and try to bend it when it's in vertical position, you can't bend it. You could stand on it and it won't bend. On the other hand, on a 2x4 that's in its what we call the plank position, this position, or sorry, this is joist, sorry. Joist position and the plank position, it will bend quite easily compared to the joist position. So the vertical is going to be a lot more. So let's actually do that. Calculate the moment of inertia for a 2x8, both in plank and in joist formation. All right, so we just plug it into the equation. So the first one is going to be 1/2 times 7.25 cubed divided by 12, and we get 47.63. Now we do that same thing for and that's in our joist formation, and then we just tip that same 2x8 on its side, and we get the 7.25 times 1.5 cubed divided by 12, and that gives us 2.04. Notice a much drastic difference. Now those numbers may not mean something, but compared to each other, that is a much larger number, and it's a lot stiffer of a shape. Now, moments of inertias of other shapes, we can get them. We won't deal with them in this class. We are going to deal with just purely rectangular shapes, which is that equation right here. On the other hand, you can get like triangles or hemispheres or quarter circles or circular sectors or circles, and they have their own equations. When you take AP Physics or a class called Statics in college, you'll learn more about how to calculate those and how to find those equations. Now, modulus of elasticity is going to be dealing with the materials. Now, the modulus of elasticity, also known as the Young's modulus, symbolized by the letter E, is how stiff something is based on the materials. So the modulus of elasticities are measured in pascals or psi, but because the modulus of elasticities are so large, they can usually be expressed in gigapascals or psis. So here's some numbers that you can look at for aluminum, steel, concrete, plastic, bone, titanium, rubber, wood, granite, diamond. Some of these are massively strong materials. You have steel at 200, titanium at 105 to 120. A lot of people know that steel is stronger than titanium. It's just titanium is as light as aluminum, but is twice as strong as aluminum. So it's a misnomer. People think titanium is stronger, and it isn't. Steel is actually stronger. We can look at different materials, and some of these are like, you're going to be surprised at like how strong bone is. Bone is up there with aluminum. And so that means your bones are about as strong as aluminum. I mean, it's not steel, but then you can look at other stuff like concrete and granite. You can see granite is a much stronger material than concrete. But you got rubber, which is ridiculously not strong, and diamond, which is the strongest material in of the known universe, and that is, way above everything else. Now, beam deflection. When we talk about beam deflection, there are two different types of beam deflection. There is your simple bridge deflection. We're going to call that the simple deflection, where you just put your beam on top of two supports and then you put your load right in the dead center halfway in and watch it bend. Then there is the springboard deflection. This is like your diving board, where you have your beam and then you have some force outward. There is no support here. This could be like an eaves on a roof, or this could be some cantilever beam. This does happen quite often. We're not going to deal with springboard and deflection. There is equations for them. We're going to deal with the simple deflection. So beam deflection. The amount it bends, so how much it bends, is going to be known as the delta max. This is the symbol delta. It looks like a D with a little squiggly on the top. It's how far down it goes. And that is equal to the force applied times the length cubed divided by 48 divided by the Young's modulus divided by the moment of inertia. So we have to calculate the moment of inertia, and you have to know the material in order to figure out what that beam is going to deflect. So let's actually do a calculation. So calculate the beam of deflection for a 96-inch 2x6 white oak plank using 200 pounds for the load and a modulus of elasticity of 1,780,000 psi. Now realize that the actual dimensions of a 2x6 is not 2 inches by 6 inches. It's actually a ½ inch on either side. So it's 1.5 times 5.5. So I want you to calculate that now. All right, so let's list our knowns. We know the force, we know the length, we know the Young's modulus, but we don't know the moment of inertia. So we need to calculate that. So we go back to our previous slides and we look at our I, which is base times height cubed divided by 12. And we plug that in, we put our dimensions in, so we know that it is, and it says that it's in a plank formation, not in the joist, so it's going to be our base is 5.5 and our height is 1.5. So we put that in, and we calculate it as 5.5 times 1.5 cubed divided by 12 gives us the 1.54. So now we can actually plug that back in. Now we know everything for our equation. We can plug it all in. Force of 200 times 96 cubed divided by 48 divided by our 1,780,000 and our 1.54. Now realize that all my distances have to be in inches, and I know you're like, well, but this is also has inches in it, pounds per square inch, and then these pounds have to match these pounds. So everything, and then these measurements are all in inches as well. If you start mishmashing units like feet or in the metrics, you start messing up your number. So this means that I will deflect a 96-inch beam, or 2x6, and if I stand on it, it will deflect 1 1/3 inches down into the floor. So here are other beam deflection formulas that there are. Like I said, there's the one. These are our cantilevered ones, and here's our basic bridge trusses. They're simple ones. Depending on the force, if all the pressure is on one end, like you're diving, then you use this equation. But if it's somewhere else, then you do it here. If it's evenly distributed throughout, use this one. Use unevenly distributed in a kind of a triangle, like snow drifts. Use these ones. If it's bending by, you have to do this. Again, these are going to be well into college level equations. You don't need to write these down, but these are where these come from, and you will learn later on in college some of these equations and where they get these numbers, like the 48. Where did that come from? And you'll learn that in AP Physics and or statics. So, what causes deflection? Well, it's what's the materials it's made out of, the shape of the beam, the force that it's applying to it, and where that force is applied. So it just depends on all those 4 factors. So if you have any other questions, go ahead and write them down and ask me in class.